So I'll be talking about spectroscopy in the Zeeman sublevels and mainly using the electromagnetically induced transparencies. Half of my talk probably some of you have already heard of, and the later half is something new and something interesting that it's not complete, but then we can always discuss about it. So we have heard about and learned about electromagnetically induced transparency by a few speakers. So it's just a very basic concept that we are using here is that if you have a 3-level lambda type system and you shine a laser, you have an atomic system where there is 1 excited state and 2 ground state. And if you shine a laser from one of the ground state, what you get is basically an absorption profile, while the dispersion looks like this. While if you come now with another laser from another ground state and a stronger one, then you create a transparency window within this absorption profile, and dispersion becomes completely takes the other form, the slope of it. And to make this EIT work, EIT we say at electromagnetically induced transparency. So to make this work, the frequency difference of the 2 beams equals to the separation between the ground state. The good part about this that if you can change the dispersion in this order, in this EIT region, the medium has very high normal dispersion, and you can control over the group velocity of light. And this is one of the spectrums that we have taken very initially, and it's quite not very like you have to do a lot of high precision spectroscopy for that. And well, I take back from this introduction. Sorry. Yes.
This beam, red beam, has to be stronger.
Yep.
But for example, in the case of they are the same. So these conditions in general.
Okay. 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 Fine. I take back to your atomic physics classes and just tell a few things about the selection rules. So if you have the laser is propagating along this direction of the magnetic field, if you have a magnetic field and your electric field is perpendicular to that, then you are actually igniting the delta M plus minus 1 transitions, which gives you this sigma line. So you have an atomic, if you have this magnetic sublevels, and then you can have the 2 sigma transitions if you have electric field perpendicular to the magnetic field. But if you have your electric field and magnetic field all parallel, but perpendicular to the propagation direction, then the only selection rules that occurs is delta M is equal to 1. And due to this transition, we get the pi lines. Now, what if, and this is the absorption profile that you get, only one of them, which we call it pi transition. Now, what we want to do is that we want to have a rotated coordinate system. We have that only when we put an angle between the electric field and the magnetic field. When we have a theta between them, that is the magnetic field is not along the propagation direction, you can break away your electric field into 2 components. And see Z, if this is the reference frame by rotated by theta with the quantization axis, then you have 2 components here for the pi and the sigma component. And therefore, in the absorption profile, you will get all 3 transitions there. Now, so far so good, but if we want to have a more crazy amount of things, that is, if we want to really have the electric field not in the plane of the magnetic field, so there is that magnetic field which is making an theta and the electric field making a phi, and then what you have is that you can actually control the amplitude of the absorption peaks by controlling the effective polarization. So you see there will be sigma and pi transitions and peaks for that, but then the electric field will look not very simple. And therefore you have contributions from your polarization as well as the quantization axis. So you can control it. So our job was actually to we wanted to know how this arbitrary polarized light be absorbed in the atomic medium in presence of an arbitrary magnetic field. So you go arbitrary on both, and what features that you can extract from the research. So this is the schematic of the experimental diagram. We wanted to do a EIT sort of a configuration over here, and we took F is equal to 2 and F is equal to 1. These are 2 ground state, and these are the hyperfine state F prime is equal to 2, and then you have a control and a probe field. And so this is the energy diagram for a lambda type configuration. The two lasers are from two different lasers. So the two beams are from two different lasers. We combine them, but we also make something like we make a linear perpendicular linear polarization. So sort of that we combine both the lasers, but then one of the lasers and the other lasers both are linearly polarized, but they are 90° to each other. So we do it in that way. And then we take it through a rubidium cell where we have a longitudinal field and we can create a transverse field. So you can change by changing the current in the longitudinal and transverse field, you can change the quantization axis B. And then by changing this half-wave plate, you can actually change the complete polarization. So maintaining 90°, now you can change the phi between them. And with these conditions, if we send it through our atomic medium, what we are doing is that we are breaking the hyperfine levels into the Zeeman levels, and you are making a number of lambda transitions. I mean, a number of lambda, you can say lambda EITs. So this is a really complicated diagram, and it takes time to actually understand. And so what happens is that if these are the three beams, which is blue, red, and green, are for the sigma plus minus and pi transitions, but both pump and probe now have sigma plus minus and pi components. So they couple to all the delta M plus minus transitions. Now, if we decompose this thing to a very simpler picture, and actually what you see in the experiment is this thing. That is, this is the probe transmission, and if you detune your beam, one of them, then you see that there are 7 peaks that rises up, while having like 45° your quantization axis, so the magnetic field is off by 45°, and your phi, that is your polarization, is at 40°. So if in this condition, if you can break up the entire Zeeman level EIT resonances, so over here you can see what I have done is that you have the 4 conditions that in pump and probe both are pi polarized, or the pump is pi polarized and probe is pi polarized and pump is sigma polarized, which is this one. And here this one is your pump pi and probe sigma polarized. So all these conditions and both pi polarized. If you can break up these things and then the sublevels, the separation between the sublevels, you get all these 7 peaks. Now this is where we understand things like that. But then it comes like, what will happen now if I actually change my magnetic field in the plane of polarization? So will I get all 7 of them? That's what we did here. So we tried to see the probe transmission while we vary the quantization axis. So due to the variation of quantization axis, I mean that the direction of theta, that is this theta angle, is changed while phi is 0. So therefore the pump and the probe, the beams, the polarization of that are linear and perpendicular to each other, but we only change the magnetic field. So it is something like this that videos will not work, but anyway, we understood. So what happens here is that first, when we came with the 0, that is theta is equal to 0, that is magnetic field is along the propagation direction, we have only the sigma transitions because the electric field is perpendicular to that. Again, when we went to theta is close to 90, then the electric field and the magnetic field, they are parallel. So we have only the pi transitions. Now in between, we have all the more transitions. That is, the point is that you have, so you see that here the pi transition, the sigma transitions went lower and lower, and the pi transition, which was not there, grew up. But then with changing the quantization axis of the magnetic field, the resultant magnetic field is also increasing. And therefore you get the peaks splitting one with the other. So this we can use to actually determine the magnitude of this magnetic field. So it's very simple that you have a peak separation. You take 2 peaks and then you can go by calibrate the separation while increasing the total magnetic field. And you can have, you can just have plot slope to that, and then you can find out what is the resolution and other things. And this is how you can determine the magnitude of the magnetic field. But then if you keep the magnetic field constant, that is your quantization axis, say perpendicular to the polarization axis, perpendicular to the propagation direction, and change just the polarization axis of pump and the probe beam. So what I mean to say, you keep perpendicular to one with the other, and then you change the polarization, keeping it perpendicular. So you just change the polarization, keeping the magnetic field perpendicular to the propagation direction. What you see here is that at phi is equal to 0, phi is equal to 0 means your EP, that is the probe, is parallel to the magnetic field. You have only the pi transitions. And now if you have the E field that is 90 degree, you again get back the pi transitions because they are parallel. But in between, when we have an arbitrary polarization, you see that the sigma peaks actually grew up. They grew up and then they vanished. So it's something like that. There is a node over here, there is a node over here. In between, the sigma peaks grew up and then it vanished. So it is some kind of an oscillatory behavior that we see here. So we wanted to understand why this is happening. And so the first thing we did is that we got to the theoretical model, to the master equation, and we took out, we plotted the total Hamiltonian. We calculated that with all the depopulation and repopulation matrices. And we considered the light atom interaction Hamiltonian, the atomic atom Hamiltonian. And we did this numerically, and we saw that if this is the experimental program, we could reproduce almost the same thing. And we took like a density matrix equation was solved for 13 levels, and we took the atomic density matrix package for that, which Professor Bhutkar has mentioned in his talk. So we used that, and we found numerically that it matches quite well. But then we wanted to have an analytical solution to that. We wanted to framework an analytical computation where for an arbitrary magnetic field and an arbitrary polarization field, and if both are arbitrary, you get completely crazy, right? And so we wanted to be a little crazy on that and wanted to have an analytical solution by a toy model. By a toy model means we took only a subset of these magnetic transitions in the Zeeman level, and then we analyze this. We have a very long derivation for that. I'm not going into that, but you can see in this publication of us. And what we achieved is that after this analytical solution, we achieved these three transitions. These three transitions means it's just A0, the central one, and the 2-1. But that is enough for actually find out what is happening. And with the toy model, when we fitted the toy model, and at some conditions of that is theta is equal to 90, that is magnetic field perpendicular to the propagation direction, the A0 amplitude, remember the A0 means this guy at the center. So this amplitude actually goes up and goes down. So this is the A0. So the central field goes up and goes down. So this A0 amplitude, which you get here, this is defined as like this whole term, where you see that there is a kind of an oscillatory term which comes due to this phi. Phi means change of the polarization axis. So you see that those nodes that we got here, if we change the phi and rotate that, then at certain point of phi, that is phi is equal to n pi by 2, the peak will not be observed and it becomes 0. So how can we get, so this is the locus of A0 that we find. Now, how can you get the direction of the magnetic field in that way? Because if this, this is a magnetic field which is at theta is equal to 90, but if you change the magnetic field, the locus will actually, the 0 points will move, the entire thing will shift. And by that way, if you change your polarization axis, and by changing in the magnetic, if there is a change in the magnetic field, you can track the movement of locus, and by that you can find the direction of the magnetic field. So we did this, and we found this is the analytical expression to that, and these are the measurement points. So at the end of this is the first part of the talk, and so at the end of it, what we got is that we wanted to get a vector magnetic field study on EIT with perpendicular linear polarization. Now, vector magnetometry means you will probably also include the entire space, right? It is not only in one plane, but also 3D. 3D, well, it's so complicated in the analytical form that we could have done it, but analyzing it and getting to a point that you understand everything was a little difficult, but that is a job to be done. Now, what we finally found out, dependence of EIT, we have found out on the direction of quantization axis and the relative orientation of the polarizations that we put on the applied electric field. So that we found out experimentally. And since they spread out with the total magnetic field, then from the relative separation of sigma and pi EITs, the strength of the magnetic field can be calculated. Now here you see that there are peaks, there are pi peaks over here for phi is equal to 0 and 90, and then you have the sigma peaks growing over. So you can get the EIT peak amplitudes show this oscillatory behavior, and depending upon the orientation of laser polarization relative to magnetic field direction. So this shows that with this relative strength of sigma and pi EIT, the direction of the magnetic field can be found. We haven't done it yet, but yes, this is possibility. And finally, we found a complete theoretical study by numerically solving this 13 Zeeman sublevels. And we have actually constructed an analytical response to the medium. So everything is there in this paper. The point is that we have this rigorous theory made, because if we really have to go to the complete topology or tomography of this thing, then it becomes, then this analytical expression or analytical, the analytical solution becomes very handy. But it is not very easy also, as you can, if you go through the paper, you will see. But that's something that in future we can simplify and do things like that. Then it will be good. Now I come to the next part, which is a bit new. So while we were doing this study, we also studied about slow light in rubidium systems, just from the concept of quantum memory. And we found out that yes, we can slow down in a V type of system, not a lambda system, what we have. So it's not phase log laser, and we can get some kind of slowdown by sending a pulse, but it has also a lot of limitations, but at least we saw that we can slow down. We also interplayed with the coherent interactions in a N-type system. N-type means one lambda and one V coupled with that. And then we can go for tuning just one Rabi frequency, just changing the coupling Rabi frequency. We can go from EIT to EIA. So this can be one of the ways that we can go from a highly transparent to highly absorbing mediums by changing just the coupling Rabi frequency, and this can be used as an all optical switch for quantum technology. This, after these studies have been done, then Saikat Ghosh's student visited us, and we were so impressed by Saikat's work that, okay, we can slow down, but can we slow? If he has stored, so can we store the entire thing? So we made a very complicated setup after my student Priyabrata joined. So this was a setup which is used, which we set up to observe quantum memory in Zeeman sublevels. Because till that time, if you want to have a lambda system, that's the best EIT or the depth of EIT you can get. So you can store for a long time, but then if you want to play it within the hyperfine levels, you have to have the EOM. So at that time, we didn't have the EOM, or we haven't characterized it. So Priyabrata found out a way that, okay, we can do it in the Zeeman sublevels. For that, we took one 795 DFB laser, and then we had both the lasers derived from one single laser. And you can see this is SAS, and then we derived both the things. And now what we are looking for is in a transition of f is equal to 2 to f prime is equal to 1 in the D1 line, and it is phase locked. So we took it through two AOMs just to compensate one with the other. One of the AOMs we can scan the detuning, so we can scan the frequency. We made it in a double pass arrangement to take care of the spatial movement of the probe. And then we also took the powers are in the microwatt region, but the pump power was much higher than the probe power. We had a resistive heater also, and we heated up to 70 degrees. We had a homemade 3-layer mu metal shield to reduce the inhomogeneous Earth's field, and nitrogen buffer gas also was used in this. So we combined both the beams. Now we took it to the fibers to make it very clean and Gaussian mode, and then we took it to the rubidium cell, and with the heater inside and everything. So we targeted that, okay, fine, we will be targeting this transition, which is, this is the coupling beam and this is the probe beam. So everything was fine, and we expected to get a nice EIT. But, well, you can always target for one, but this seems like something that we got in the, when we want to buy something in the mall, that is buy one, get one free. So we got one free. Okay, fine. But then we thought, like, when we got one free, why not we try to understand why we got this as free? Because there was no advertisement as such. So we tried to do some spectroscopy of that. I mean, we just find out that, okay, what will be the changes to be done in this double EIT system if we change the magnetic field? So with the do photon detuning, if we change the magnetic field, we immediately understood that, okay, the splitting is going further apart and the peak height of EIT1 increases while the peak height of EIT2 decreases with the increment of the applied longitudinal magnetic field. So you can see that this, while we change the total magnetic field, the EIT1 peak and the EIT2 peak, they split apart, and then they are also following some linear relations with them, and also going down in the intensity as we increase the magnetic field. So we immediately understood that, okay, if since there is a slope of 1.42 and a slope of 0.74, at least we can find that from the peak shifts, then at least first of all, there is no one lambda system, but there must be two lambda systems. That also was not very, that's not also too tough to understand. So we wanted to know the origin of this double EIT. So this was our targeted system, and we got the EIT1 of that. But the other EIT, if you just measure the slopes from here, the other EIT has to come from a system like this. This is also a lambda system, but not as sigma plus, sigma minus. It is sigma minus, but with a pi transition over here. Now, how can you get a pi transition? There are only two ways that you get two EITs. One of them is delta MF is equal to 2 if we have delta MF is equal to 2 in the two ground state. The other has two possibilities, delta MF is equal to 1. So either it can be 0 to 0 plus minus the ground state, or plus minus plus 1 and plus 2. So these are the two. Now, which one of these two EIT systems is effective? So is it like there is two independent EITs working, or one of them, or what is happening here? So first of all, we have to understand that why this pi transition came. We never had any pi, we never thought of any pi transitions in our system, and we wanted to avoid that, but we couldn't. So how does this pi polarized control come? So what we did is that from the peak separation, we actually applied the longitudinal magnetic field, which we already had. And when we applied the longitudinal magnetic field from the peak separation that you get, what we can find out, and you included the other, what are the things that can go wrong? Only inhomogeneity is your Earth's magnetic field, and your heater, is the heater magnetic field, magnetic or not. And so we, from this plot and fitting that, we understood that the Earth's transverse magnetic field is 17 milligauss, longitudinal component is 18 milligauss, almost of the same strength, as well as this controller on, and controller off means the temperature controller is off. And then also we got, by plotting another one and fitting it, we got 3 milligauss, which was magnetic field was highly homogeneous. So yeah, our new metal shield is not good as that. It's homemade. So at least we understood that there is a fault of the system, as well as the heater is also giving out a magnetic field. So, okay, fine, we have to change it. And so we also understood that, okay, it is not like we are giving a mu metal, we are giving a pi control field, but as you can know that when you have an arbitrary magnetic field, when you have two magnetic field in a component, so it's a resultant magnetic field, your quantization axis is not along the propagation, it has been tilted. And this part of the electric field gives you that pi control field. But this was good that we understood the origin of double EIT. We wanted to do a little bit more. What happens is that, what happens to the line width of this double EIT? So as this is the double EIT that you can get. This is EIT1, this is EIT2, and these are the pump powers. So we go on increasing the pump powers. What is expected is that both EITs will show normal increase in line width because they are Lorentzians. So we tried to do that, and what we got is that for EIT1, when we increased the pump power, so we got a kind of a slope which is normal to that. So EIT1 shows a normal linear power variation, having a y-intercept at 9.15 kilohertz. So if there is no pump power, you get an intercept of 9.15 kilohertz, and this value comes very close to the intrinsic ground state coherence decay rate, which is like 4.57. Now, coherence decay rate, absolute coherence decay rate is a bit lower than that, but you have inhomogeneity, so at least half of this is your coherence decay rate, and some publications have said that you can go close to 4. But then what happens to EIT2? Because EIT2 is almost insensitive to power broadening, and with a constant of 5.91 kilohertz plus minus 0.28. So this is not the feature that a Lorentzian will do, but can you really can you really see what is happening? Because you should have got the same kind of feature. Now, one thing we understood that as the pump of lambda1, that is the lambda1 system means this lambda1 system, and gets stronger than the other one, the influence of lambda1 on lambda2 also gets large. So while increasing lambda1, the one with the lambda2 will go down. And so lambda2 with the ground state of MF plus 1 plus 2 will prevail over the lambda2 or the ground state of MF 0 and 1. I mean, what I mean to say is that you have two ways that you can define the lambda2 system. So is it like two lambda2 systems operating at the same time? So you have these two combinations, and remember that what I'm doing is that I'm increasing the intensity of this pump laser. So this transition is getting stronger and stronger, and that will make the other transition weaker. This transition is more probable that it will not happen in this way. So we are only strengthening this transition. So in this way, we can eliminate that we are probably looking not as independent lambda systems, but rather as interacting lambda systems, making a 4-level tripod scheme. So the point is that when you are increasing this, the omega 2, the Rabi frequency of this will go low, and which is happening here. And that's why we say like it is not like lambda 1, lambda 2, two independent one, but it's a couple system which is working and making a 4-level tripod scheme. But this doesn't really tell you why would I get this one. It might happen to lambda system, but they are Lorentzians, and so they will have normal increase in line widths. So we went back to our theory and to find out this reason behind this abnormal behavior of E2 line width. So what we did is that we understood that it is a tripod system. So we took a tripod system like this, and then we then we worked out our Hamiltonian of this atomic system in the interaction picture after rotating wave and dipole approximation. So this is the Hamiltonian that we have worked out for this tripod configuration. I'm not going through the entire theory, which is quite rigorous. But then after that, from the Liouville's equation of motion, as we do for the other cases, we got the time evolution of density matrix elements. Then we solved for the steady state linear susceptibility, and we incorporated the decay rates due to the inhomogeneous broadening mechanism present in the medium. So inhomogeneous magnetic fields, we have included that, buffer cell effects, and all those things we have included. And since we are doing the experiment in a vapor cell and in a hot vapor cell, so one photon Doppler shifted detunings are also included in this susceptibility due to this hot gas. So what finally we got, the susceptibility relations such as this. And so you can see here that the lambda, if lambda 1 is very much greater than lambda 2, then this lambda 1 will have an effect of lambda 2. So this lambda 2 term is very small. So what we can do is that we can Taylor expansion this. So we took common of this term, the first one and the third one, and we took them out, and then we Taylor expanded what is left in lambda 2. So what we had here at the end of the Taylor expansion, after taking just the first two terms, is that you can break it up into chi1 and chi2. These are the susceptibilities. And for the EIT1, we got a chi1 expression, which is as this one, which is an expression of a Lorentzian. If you can take out, we have to do a little bit more work, then this will becomes a Lorentzian. And then from a Lorentzian, it will have a linear power broadening, which is inherent for a Lorentzian. Now, I mean, the absorption of the probe beam is proportional to the imaginary part of susceptibility. So this is the imaginary part of susceptibility. And for EIT1, this chi1 works, and it will have a linear power broadening. Whereas this chi2 takes a very complex structured form. This is not sort of a Lorentzian, which I mean, we can say that this is what gives rise to EIT2, but its line shape deviates from Lorentzian at higher control power. Higher control power means as we increase this one. So EIT2 do have present, but the line width of EIT2 remains immune to power broadening. Now, this is some sort of understanding that we have till now. So I won't like demand that this is probably the only understanding. So we are still working on it, but at least till this point, we understood the thing. So, I mean, I won't conclude this because there was really no conclusion in this point, but this is a sort of a middle conclusion or a part conclusion. So my acknowledgement goes to my students for the first work. It is mostly done by Bankim and Arpita, and they are already outside in doing their postdocs. And Priyobroto and Nawaz, they are working in the project. Nawaz is working on structured beam as iHub postdoc, and we have Sunil and Manisha working on collision studies. That's a different thing. And well, if you want to have PhD and postdoc, we have PhD and postdoc positions in quantum sensors or cold atoms or just spectroscopy. And you can apply to my email ID. This is my email ID. And this is what the lab looks like while Bumkim was working. And what Priyabrata did is that completely washed it out, made his own setup, and he's happy about it. But very importantly, we are seeking faculty positions. And this is important because at the end of the day, you need jobs. So yes, there is a faculty position advertisement in Saha Institute of Nuclear Physics. The last date is July 31st, 3 p.m. So be very careful. And we have the group, we have many faculty positions, but in the group B, we have 2 posts. It's not decided which one goes where. So there can be 2 atomic physics or at least one of them. So yes, 35 years is the age limit. This is important to remember. And we only need 2 years of postdoctoral experience. So apply, please ask your friends, students to apply. Thank you.
For the talk. Floor is open for questions.
Person with looking something, he's in which position?
He is in a position to dictate. He was.
So particularly this this double EIT where you, yeah, so exactly, like you can go to that slide. Yeah. So here you're saying that like one seems to be like the power broadening is not there. So is this some sort of a common mode Stark shift cancellation, or like, is there a simple way of understanding it?
I don't know.
So
we went through
because
this.
it can be very important, right? If you have by increasing power, if you do not see power broadening, that might be very exciting actually in many ways.
Yeah, we only got to this point that yes, we have an expression which is very complex and you cannot debug it through that. But definitely, I mean,
But experimentally also you do not see, is that like in the width you do not see?
Yeah, you do not see.
Flattened. Huh?
It's completely flat. So we wanted to go and do something else. We got something, and then this was, we actually didn't expect to get.
And this is the full width at half maximum of the baby peak.
Yes, 0.28 kilohertz within that. Okay, something that I didn't show here is that when I turned off the longitudinal field, it was only the Earth's field. Okay, so Earth field means these values. So this is almost like the longitudinal and the transverse field for the Earth is almost the same value. So the quantization axis will be close to 45 degrees. Under this condition, if I do this same study, then it's not like it's immune. So you do have the EIT, both the EITs are of the same strength, almost at the same strength, and they do vary with the pump power. So this feature that it doesn't change, it's not like that when you have a really 45-degree quantization axis, you have turned off your longitudinal field. So yes, if you go to very strong longitudinal field, then this will slowly diminish and become very, very small. That is true. But with this, with the magnetic field that we started with, so sort of, yes, 36 milligauss, that was just an arbitrary magnetic field. Then we saw this feature. And then if we go to very strong magnetic fields, this feature diminishes off. Just because, see, the point is that you are pushing your quantization axis along the propagation axis, so the EIT2 vanishes. But that was also understood, only this thing was not understood. Why would this happen? It is also understood that EIT1 is having an effect of EIT2. So it is dominant, this lambda system is dominating on the other. This was also understood, but how would this feature, this is only, I mean, this feature we had to do this entire derivation just to understand this feature. And we came to this point, till this point, that this does not give you a Lorentzian kind of shape. This is something abstract. And maybe that is the reason that you do not get a power variation.
So I have one question from the first experiment,
Yes.
where you showed the EIT peaks for various 5 values in the first, when you started the present. Yeah. Yeah. The next slide also you can show the EIT peaks. Yeah, this one. Yeah. So if you see the rightmost or the leftmost peak in the 4 sets, there is an asymmetry, and this asymmetry changes as you change the 5 value.
Okay, you see
Yeah,
this one.
yeah, and then it becomes completely
the
opposite to,
the slope.
yeah. So 2 questions. One, why is there an asymmetry? And second, why is that asymmetry changing by changing
Okay,
5?
I can tell you something that these peaks doesn't come on this background. There is a Doppler background on that these peaks come. So we just
Okay.
subtracted something with this. It's not like really a physical function. And well, because it is riding on the Doppler peaks, Doppler, then maybe the asymmetry came for that, but
Okay.
I have no idea other
Okay,
than
okay.
this.
Okay. Thank you.
Okay. If there are no more questions, we can move to the next talk. We'll thank Professor Shankar again.